Good morning, everyone, ladies and gentlemen, dear friends from Peru and other countries. On behalf of AIRBUS, first I would like to give warm greetings to Conida and General Tuesta. It is a great pleasure for us to participate in the fourth edition of the Conida seminar. This year is a webinar. I would have preferred to give a talk in Pucusana, like in every year. AIRBUS has been with Conida through PeruSat and also participating in the workshops by Conida. This year, AIRBUS will dedicate to two issues: the use of space images that my colleague Alfonso Casado will introduce, and today I will refer to the interplanetary missions concerning the issues that I have already presented in previous seminars. So with the mission of observations, communications, and space technology. Well, in order to introduce myself, my name is Josian Fabrega. I am the Director of Development and Sales for the Space Systems in Latin America, especially on the Pacific side. For 30 years already in the space industry. I was the director of the program 3 times for the Interplanetary Missions now and the European system, the European agency, and I have been working in the direction of sales since 2012. And I signed, yes, the PeruSat agreement with Conida. Well, today I will refer to a very interesting topic for the specialists, very interesting for the big audience. The interplanetary missions in the solar system. I will give an introduction first of the missions that have already been launched and are in orbit, the experience of AIRBUS. It is the European champion for these type of missions. Then I will give an explanation, yes, about the challenges and main aspects of the design of the interplanetary sounds. And the ones that we have to deal with are of the same type. Then I will give two examples. One example of the Bepi Colombo mission and another example which is a mission to Mars, which is very special because in that mission we will have to return to Earth with part of the soil from Mars, and then they will be analyzed in our laboratories on Earth. The first question is why? To develop missions, interplanetary missions. The reasons are multiple and essentially interesting for the scientists. The first reason is to explain the creation of the solar system. Recently, new theories have emerged to explain its creation, yes, of the solar system, and what is the role of the planets such as Saturn and Jupiter. Without the planet Earth would not have existed as we know it. And then to analyze the behavior of the other planets in an extrapolar way. As the case, this is an interesting case for the Earth. For instance, Mars or Venus, there is a very particular interest. Obviously, an issue that is very current is the search of life and the search mainly of water as liquid and life and for because of the recent discovery in Mars. Another possibility is the analysis in situ, as we have done with the Rosetta Sound in a comet, or other missions which are missions that we are developing currently, such as the Mars Sample Return. And the idea is to return, yes, with a piece from the soil, something from apart from the soil of the soil of Mars. And on the other hand, we know, due to the public, of the missions that make people dream in the world. These missions where the vector is the communications in the social networks. So the first European mission to Mars was called Mars Express. It was launched in 2003 and it is still working perfectly after 17 years in the orbit of Mars, mainly for cartographic studies or use, the study of the atmosphere, the search of past marks of liquid water on the soil, ice on the poles, and yes, the search for some spectacular marks in this environment. Another iconic mission was Rosetta, developed by this was launched in 2004 in order to study and to approach the Chury comet. The objective of the mission was the analysis in situ of the chemical composition and the structure of the comet, also the study of the tail and the length of the comet. So there was a landing on the core of the comet for the analysis in situ. The mission JUICE is for Jupiter. It is a mission to study the frost areas, the frost moons of Jupiter, such as Callisto. We know that there is an ocean in Europa of about 50 kilometers, and an objective of the mission is to quantify possible marks of elementary life. This mission is undergoing by AIRBUS. It will be launched in 2022, and 7 years of traveling, and it will be around Jupiter for a mission of 2 to 3 years. So who are the main players, the global players for interplanetary missions? Historically, I should say that the interplanetary missions, this started in the race to the moon, and the two initial players and essential were NASA and the POSCO Moscow. So in the 70s or 80s, then the European Space Agency started, and then the Japanese with JAXA. They were also important players. And more recently, I can mention missions from China or India, and also a mission with a company from Israel called SpaceTech. So from all of the agencies that have made launches, such as JAXA or the Russian one. These are national agencies in general under the state administration with state funding. The only company that has been able to launch a mission privately is this company from Israel, SpaceTech. And the reasons is because these missions are very costly. Just to give you examples, for instance, the Rosetta mission cost to the European agency around 1 billion euros, and that magnitude is also, or around that amount, also for a Jupiter JUICE mission, and it will be the same for the EpiColombo mission to Mercury as well. So some background. In the space era, we have somehow launched 264 sounds, interplanetary sounds, and that represent somehow the 3-4% of all of the satellites that have been launched by all of the missions in communications Earth observation since the start or the end of the 50s or beginning of the 60s. We can observe that the rate of success has been improved little by little. Yes, little by little. And it is around 59%. That means that more than 1/3 of the missions have been, and it's true, the most of the interplanetary missions are very complicated. Or as we can observe in two essential players, the United States and Russia, and maybe a little bit more than 100 missions, we can observe that the United States are the only ones who have launched sounds to all of the planets or other bodies in the solar system. Russia has developed a big number of missions, but suddenly the effort of the Russians was focused in the 60s, 70s, and 80s, and we can observe that currently Russia schedules very few interplanetary missions with what we're capable of doing during the race to the moon. So, as I have explained, Japan is more recent. Europe, the European Space Agency, has developed several missions, and it has a very important role in the current missions. I could say the same for Japan, that has not developed as many missions as Europe, but it also has an important role in this scope, in this environment. China, India, and Israel have put their efforts more recently, and especially in other missions. As a European, let me focus on the missions developed by the European Space Agency. This slide shows all of the interplanetary missions in the solar system, obviously, that have been developed by ESA since the 70s. As you may observe, AIRBUS has been a fundamental player for all of the missions, and particularly AIRBUS has been a main contractor, or for maybe if not for all of them, but for most of the missions. So in the interplanetary missions, AIRBUS is the European leader, and it has a global ranking. I cannot give in 30 minutes a presentation of each of the interplanetary missions in this slide, but I will give a specific focus on the Bepi Colombo mission and that we launched in 2018. In a general way, several aspects of this or remarkable aspects of the design of the interplanetary missions that we observe for each of the missions that I will summarize with these slides. The first thing is the setting of the mission, because there are missions that are somehow simple. We may have a single sound, for instance, to the moon, or we may have more complex sounds that have several modules, several sounds. This is the example of the Bepi Colombo mission. It has several modules which are more complex. Those modules may be a orbiting or a landing, including a rover, such as the missions to Mars currently. NASA or ESA are developing systems, a rover system, very interesting for the analysis of several sites, several locations in the planet. So there are also other specific practices for such as soft landing, such as in the case of Mars. Most of the Mars missions that failed, they failed because the landing was very complicated. So for other missions in Mars, they will have to be small, and the systems only with a parachute are not enough to secure the landing on the ground. So another aspect, very dimensional, I could say, for the trajectory of the missions, the sound from the Earth to the target. The problem we have is that the launching mass is limited due to the capacity of the launchers. So we cannot have a direct ejection from the Earth to the planet. We can do it. We can have an example for missions to Mars or to Venus or other planets. These, for the other planets, it may be very complicated due to the limitation or the limits of the launchers. So most of the interplanetary missions we use the gravitational assistance that we use other planets to accelerate or to stop, to brake. It's free, but there is a price to pay. Then we have to, if we don't pay it in fuel, then we have to pay it in the duration. In other words, we need, or it requires, to use the gravitational of gravitation of the planets, the gravity of the planets, or going around other planets. And this has, as a consequence, it's a long mission. For instance, in the Rosetta mission, the mission since its launching to the arrival to the Chury comet was of about 10 years. And in the trajectory of the interplanetary sounds from the Earth to the target, they are also conditioned by the launching windows, because we cannot launch whenever we want. We have to have an interplanetary conjunction For instance, from the Earth, between the Earth and Mars, between the Earth and Venus, or Mars or Jupiter, to minimize the maneuvers and the amount of fuel. So we have to launch at very specific periods. That's what we call them launching windows. For instance, in the case of Mars, we have around 18 months, and the change for the other planets in the solar system. During each of the missions, the assistance from the sun, it may change in a very meaningful way. And we have, as a consequence, many variations of the solar flow. For instance, in the case of Rosetta, through which the trajectory was to Jupiter, we have a solar factor between the Earth orbit and the Jupiter orbit of a factor of 25. So we have to refresh the area so that it may be robust to the flow variations. Consequently, we have to design a robust thermal subsystem for considering those changes. Also, the solar flow has a huge importance to dimension the proper solar panels. In this, yes, there is a particular complexity due to the European missions. The European mission cannot use nuclear energy on board for interplanetary use. We also have wide variations of resistance between the Sun and the Earth, because in this trajectory, and they result in extensive durations of the signal transmission. For example, for a mission with Mercury, we should have up to 12 minutes between the emission of the signal from the Earth or the sound. This is an exemption. For missions that reach Jupiter or farther than Jupiter, so it requires, it's at 5 astronomic units, so we have more or less 40 and I would say 50 minutes of a trajectory and with this signal. In other words, due to the emissions, due to the duration, it's impossible to make use of the sound, so we have to implement an autonomous capacity, a very important one, a mechanism of resetting if there is any problem. That's the reason why, not to say all of the missions, have several redundancies on board of all of the electronic equipment. Another remarkable aspect is this distance between the sun and the target for proximity missions, for orbits, to be in orbit or to land on the target. In order for most, let's see, not all of them, all of the sounds, so we require autonomous navigation that may be somehow complex, and there are additional difficulties in the case of the comets or asteroids. For instance, in the case of Rosetta, we didn't know before the launching the shape of the Churi that we can observe. It looks like a boot, has the shape of a boot, and since Rosetta has a lander, we had to select a location for the landing that was not known during the design of the sound. So So there are means of navigation on board that allow to correct the trajectory of the sound around the target, and that is also very complex. Specificity in this mission to Mars is the problem of the atmospheric reentry that requires special precautions to ensure a soft landing with the lander and to prevent the failures that we have known in the past. So the interplanetary missions, as I have stated, they are very costly, but they are also an axis of global cooperation, and in this regard I will present in a summarized way a very emblematic mission known as Bepi Colombo. The Bepi Colombo mission, it is a joint mission to Mercury between Europe and Japan. And Europe and Japan have each one a specific module called the MPO for ESA, which is an orbiter around the Mercury planet, and another module called MMO, which is an orbiter magnetospheric, developed by JAXA. A specific difficulty of this mission is that both modules will be launched, as we will see later, with a single launcher that will require additional modules for the trajectory up to Mercury. AIRBUS is the main contractor responsible of the design, the complete design of the system, of the sound that we will present right away. So why going to Mercury? First of all, Mercury is a planet for which very few missions have been developed. So this is the third mission to Mercury. The first two missions were NASA missions. The first one was the Mariner 10, launched in 1974, and Messenger, that was launched more recently in 2008. The objectives, scientific objectives of the mission, of the Bepi Colombo mission, are linked to the former missions to complement important aspects. The first objective is to investigate the creation of a close planet to our sun. I remember that Mercury is the one closest to the sun, and it is around 0.34 astronomical units. In other words, around 50 million of kilometers. To study the planet, its shape, structure, geology, composition, and craters, its exosphere and its magnetosphere, with the Japanese mission is also to study its magnetic field, its exosphere, so with which we will try to explain the origin of such field. We also have to research the polar or the extremes, and another additional objective is to use the mission to test again one aspect which explains the theory of relativity, general relativity of Einstein, which is the precision of the perihelion in Mercury that cannot be explained with the Newton mechanics. The Bepi-Colombo sound is a very complex sound comprised by several modules. The two essential modules are the MPO and the MMO. But if this looks simple, due to the proximity of Mercury, it's complex to go to Mercury and to orbit around Mercury. And the trajectory to go to Mercury, it requires additional modules, particularly the module called MTM, which is used essentially during the whole trajectory for maneuvers so that the sound will be captured by the gravitational outside exterior of Mercury. So there is a technique that I will explain afterwards. So a great difficulty to go to Mercury is the stopping that we have to do. The Earth orbit around the sun, it has a speed of 30 kilometers per second, and Mercury, which is closer, has a speed of 48 kilometers per second. So one of the difficulties to go to Mercury is to brake efficiently so that the sound may stop, otherwise it may crash against Mercury. So we have to gain somehow 7 kilometers per second and to brake every 7 kilometers per second. And we cannot only use one single module. We have to use, as I mentioned from the beginning, the gravitational assistance. The disadvantage of the gravitational assistance is that the duration of the trajectory will be longer, and in our case will be of 7 years, and we will have a total trajectory of 8,500 million kilometers to go to Mercury, to compare that to 6,500 million kilometers that were for the Rosetta mission to find a comet that was located in an orbit far, far away, close to Jupiter. So this proximity of Mercury is not a simplicity for the mission, just the opposite. The two modules, quote unquote useful modules, if I can call them that way, they are the MPO, the European module, and the MMO, which is the Japanese module. Without going into too much detail, the MPO has a payload of 11 instruments, scientific instruments, some of them with multiple sensors, and it will be located its arrival in a polar orbit of 480 kilometers multiplied by 1500 kilometers of altitude. In other words, that to go toward its orbit, the MPO requires a capacity of 1,000 hours. So it's through its own. So this orbit will be orbiting around the planet to be able to observe it constantly. It is a great challenge because around Mercury we have solar flows that are 10 times higher than around the Earth, and the infrared radiation of the sun and the surface of Mercury make it so we have a infrared radiation 20 times higher than around the Earth. So in other words, we have a temperature of the level of the sound of one of the external devices that can go up to 400 degrees Celsius. The design of the solar panels for the MPO and the antennas and the thermal shields, they require special dedication. For the Japanese module, we have 5 instruments, scientific instruments, dedicated or devoted to studying the magnetic field of Mercury. So it will be gyro stabilized, and it will be in the polar orbit, as we observe also. That means the MPO should have its own system to go to its operational orbit at its arrival to Mercury. With the two modules, the MPO and the MMO, the complete sound I will rate it as train. It also uses another module called the MTM, which is a transfer module that will be used during the trajectory. So once they are around Mercury, we will split the MMO and the MPO from the transfer module so that each one will take a position in its operational orbit. In other words, the MTM is a logistic module that we use from the launching up to the split, the final split. And once it's ejected in the orbit around Mercury. The MOSIF is a particular module that has been necessary to protect the MMO due to the position of the MMO in the tomb, in the object, and that requires a shield or protection due to the levels of the solar flow and the infrared that the MMO will receive during the flying phase, because the MMO is a module that will be on top of the train, to call it that way, of the BP sound. The sound in small amounts, figures, we can see the illustration, the drawing. It has a diameter of less than 4 meters, a height of more than 6 meters total. In the lower part, we may observe the detail of the MTM module, and on top we will have the MPO module, and totally on top of the sounds we will have the Japanese module, the MMO, and the MOSIF as well, that have this conic shape. The sound in total has a dry mass of 2600, 2670 kilos, for a humid mass of almost 4,000 kilos, more than 4,000 kilos. So that means that we have around 1,500 kilos of fuel on board, and as I said, this is not enough for all of the maneuvers. That's the reason why we use the gravitational assistance that we will see, or the photo in the. This is the core. It is in a clean room of the complete sound, and if I remember correctly, the this photo is relative to a test acoustic test in the acoustic chamber of the complete sound. For this trajectory of the Epicolombo, obviously it is a very particular and complex mission. The launching of the sound, it took place in October of 2018, but we will reach Mercury by the end of the year 2025. In other words, 7 years of trajectory to go from the Earth to a planet very close to the Earth. In order to do that, in an additional way from what I have mentioned with the carburant we have on board, the coolant we have for the modules, so that they are independent, we need to have 9 maneuvers of gravitational assistance to reach, quote unquote, without any problems to Mercury, and they will be done progressively between the phase of ejection and then interplanetary, the phase of approach to Mercury, and then up to the phase of orbit of Mercury. We will see a short video that summarizes the whole trajectory in the next video. This video of the Epicolombo trajectory was produced by ESA. We can observe 3 planets, the Earth in blue, Venus, and the white one, Mercury, around the Sun, orbiting between the Earth and Mercury. The launching was in October 2018, and with the first gravitational assistance by using the Earth. The second maneuver uses Venus. The third one as well in August 2021, Venus, and then all of the gravitational maneuvers, the next following ones, will use Mercury. We will have more maneuvers, closer and closer, to ensure the final ejection into orbit close to Mercury. So that means in total we will have 6 maneuvers of gravitational assistance, so that in the end the vehicle will be orbiting around Mercury, and with an arrival in its orbit with the separation of the modules, the MMO and MPO, by December of 2025. So later, we will be inviting you for December 6, 2025. I would like to now have a small video of another mission developed by AIRBUS, which is the Mars Sample Return, a mission of the European Space Agency and the North American Mass. The objective of this mission was to go to Mars, to take a sample of the Mars soil and to get back to the Earth to analyze that sample from Mars. In other words, this is an interplanetary mission more complex because we have to go, but also the return to Earth with some in one part of the vehicle that we have launched initially. This video shows the design of the sound. Its trajectory is the going and the return. The sound will be launched in 2026 and a return to the Earth in 2031. So this approach to Mars, since we may have a direct ejection to Mars with the rockets we have without using the gravitational assistance that the Bepi Colombo mission, as I showed, which is an additional source of complexity. In other words, there are certain things that are simple to go to Mars, but there are other things that are more complex that we have to analyze. The Earth Return Orbiter. Landing in 2028, sample fetch rover. It will return to the sample retrieval lander with up to 36 tubes, which will be launched on the Mars Ascent vehicle. Earth Return Orbiter will capture them from Mars orbit in a container. The samples are due to land back on Earth in 2031. AIRBUS. Well, we are at the end of my presentation, and I thank you for your attention. Thank you so much. So let me invite you to the launching of Jupiter Azimuth exploration in 2022, the arrival to Mercury of the Bepi Colombo in 2025, and 2026 for the launching of the Mars sample return, which are 3 of the missions that for us Europeans are of great interest. Thank you so much, and goodbye.